Hi everyone, my name is Wenli Mao. I come from University of Manchester. I'm currently the PhD student supervised by Professor Hector L. Quevedos and Dr. Andres Colini. Today, my project is about the numerical study of axial flow-induced vibration for nuclear reactor applications. Here, to do the numerical study, the software I use is the Solid4Foam, which is a toolkit based on the OpenFOAM. And for the nuclear reactor applications, here in my project, I've mainly focused on the fuel assembly. Then I'd like to share something about the background. So why the flow-induced vibration problems of the fuel rod assembly in pressurized water reactor matters. Just imagine in the nuclear core, when the coolant flows through the fuel assembly, the fuel rod will vibrate, and then it will cause the crack of the fuel rod, and then even lead to the fuel leak. So the gravity rod floating wear, which caused by the flow-induced vibration, it accounts for 74% of all the fuel rod failures worldwide. So for the nuclear safety concern, we do this FIV investigation. I've listed several FIV failures happened worldwide, like for example, the first one, 1972 to 1976, the Welfare Nuclear Power Station, which supply electricity to Manchester and Liverpool, which is beside my university, I have to say. It met the pipeline wear and performation due to FIV. And then I also list several other gravity rod floating wear cases. You can see whatever their fuel assembly design, the 16 plus by T16, 17 plus by 17, and whatever the fuel assembly manufacturer, like the combustion engineering, the Westinghouse, the Siemens, and whatever the location of the nuclear station, like in UK, Korea, USA, and even China. A very recent failure happens in 2021, July, Taishan, China. It leads to the shutdown of one reactor in Taishan nuclear station for 1 year to do the repair. So that's why you can see from decades ago to very recent 2021, the FIV problems always happens and affect the nuclear safety. So that's why we do this investigation. I've listed several pictures to show what is gravity rod floating wear, and you can see it here. You can see the wear features here. In my project, I investigate the effect of rod tip type, the flow direction, the Reynolds number, the fluid type, and temperature. What's their effect on the FIV phenomena? I'd like to share something about the fluid-solid interaction knowledge. Here the solid domain, which is the fuel rod. We view it as the incompressible and elastic solid. The fluid domain, because here we firstly just consider the vibration. So we view it as the incompressible Newtonian fluid and isothermal. Here is the iteration step for fluid-solid interaction. For the coupling method, we use partitioning method, which means the fluid domain and the solid domain will be computed separately and change the parameter in the interface. The OpenFOAM, the software, as I just mentioned before, I use the OpenFOAM toolkit Solid4Foam. The turbulence model, what I choose is the Urans Reynolds stress model, the LRR model. Why I do this choice, I will have a slide to present the reason in the following slides. In order to save the computational effort, the high Reynolds number model with the wall function are used. Then here is the experimental test rig. I will use the experimental data produced by the thermofluid group in our team in University of Manchester for validation. Also, some additional data generated specifically were also used to support my personal numerical modeling. You can see the schematic representation of the test rig in our experiment of the University of Manchester. There are water tank, pump, valve, the test session. The water comes from the tank, go to the tube, and pass away from the test session from the bottom to the up, and also we have another flow direction from the up to the dip, from the up to the bottom. You can see here is a video. It is recorded by PIV in our lab. You can see the vibration of the fuel rod, and we used PIV to do all the recording and post-processing. Then, as I stated before, the turbulence model I use is the Reynolds stress model, RR model, and why I do this selection. You can see I do the turbulence model assessment, compare the eddy viscosity model, the K omega SST model, and the Reynolds stress model, the RR model. The displacement have around 20 times. This case, it takes the upflow, the 16.8 thousand Reynolds number as an example. You can see their displacement difference has 200 times difference. That is because the Reynolds stress model, it doesn't have any assumption. It derives the transport equation for the Reynolds stress tensor directly from the Navier-Stokes equation instead of using any assumption. So that's why it has more equations and can provide better results than the eddy viscosity model. Also, this one is only 16.8 thousand. I have a list of the cases, like 20.7 thousand, 36.4 thousand, and difference would reach like thousands of times between two turbulence models. And somebody may ask why you choose the URANS model, not the LES. That's because even the 5-second data I produce, it needs like 16 cores in HPC, run for 4 to 5 weeks, because it's a two-way FSI. It solves the fluid domain, solves the fluid domain, and it do the iteration in their interface. So that's time consuming. So that's why we choose URANS, not the RES. Then I present some results. For this one is the upflow from the free end to the fixed end. You can see the displacement flow. You can see the left one is the displacement. The right one is the frequency. The Reynolds number range is 16.8 thousand to 51.7 thousand. The largest difference between the simulation and experiment of the average frequency is 0.1 hertz. The error is less than 30%. So that can show that our numerical methodology can simulate the two-way FSI of the fuel rod. And the most difficult part here is the vibration of the fuel rod is purely excited by the flow. There is no external force, no human force, no initial force. Just imagine it's steady flow at first, and then it become unsteady just because of flow-induced vibration. This process is difficult to simulate. Actually, in our large project, we also have some teams from the research institute from Europe. They also try to simulate it using Star System Plus or ANSYS, but their conclusion is they simulate no vibration. So that's why our team, we use OpenFOAM. It's more flexible to help you do all the settings, edit all the settings. And finally, we simulate it, and it can match with the experiment very well. I think that's why OpenFOAM is very essential for our researchers. Then there are several plots showing the compression between the experiment and simulation. For the left two plot, it shows the points are the experiment, lines are the numerical result. You can see it can match very well. That means the velocity field between the simulation and the experiment can match where. Also in the middle, you can see the velocity field pattern, and also the color of the field road shows the displacement of the field road. Also some Q-criterion plot, it shows what the vortex looks like around the field road. This one is just the case for 16.8 thousand. I have a list of cases, but due to time limitation, I only pressed one. There is a video. You can see that for the upper flow, Reynolds number 25.8 thousand. The Twins model, Reynolds stress model, ARR model, software selects for foam, and you can see how the velocity field changes along time and how the field road vibrates along time. The color of the field road represents the displacement. You can now the displacement is small, but it's relatively small. But when we change the flow direction, you can see very obvious vibration. That's why we do some investigation on the flow direction. Here, yes, another flow direction, the downflow, which we change the flow direction from the fixed end to free end. And the red points are my simulation results. The black points are from our experiment. You can see the middle points, it can match well with the experiment. The first one, the amplitude is just half. I think the possible explanation is the wall function and the high Reynolds number stress model, which I employ, cannot handle such low Reynolds number, which is 16.8 thousand. And we meet another problem that when the Reynolds number larger than 31,000, in the simulation, the field road will hit the wall and it stops. Just imagine when the field road in the experiment vibrates. When it hits the wall, it will continue. But in the simulation, when the field road just needs to touch the wall of the tube, the mesh becomes so distorted, so it will stop automatically. It's a video for the field road vibrate in the downflow. And you can see the obvious vibration of the road. Just imagine it's very steady flow at first, just because of flow-induced vibration. Just because the coolant flow pass away the field road, it vibrates a lot and cause the crack of the field road and even the nuclear field leak. So that's why we care much about this phenomena. You can see the vibration is obvious, and the color of the field road represents its displacement. So why we do this flow direction research? You can see the left one is the displacement compression for the upflow and downflow. The right one is the frequency. Frequency always matches where, but for the vibration amplitude, which we concerns the most, even under the same Reynolds number, that means the velocity is the same. We only change the flow direction. The vibration amplitude will differ 2 to 10 times. So that's a very exciting finding. And it can instruct the nuclear company to do some improved design on their future design. Then I'd like to do the dimensionless parameter study. So what is this dimensionless parameter study here? The dimensional analysis suggests that the dimensionless root mean square displacement depends on two dimensionless group, which is the Reynolds number, and another one, this dimensionless parameter. A couple of recent studies refer this as Cauchy number, but it's just in aerospace studies, aerospace engineering. In our nuclear engineering, my study first investigate this dimensionless parameter and find out its effect on the FIV phenomena. In the earlier compressions and the experiments, by maintaining constant fluid properties and changing the velocity, the values of both dimensionless groups will change at the same time. Here, the effect of the Cauchy number is isolated by changing both the fluid viscosity and the fluid velocity, so that the Reynolds number can keep constant, where the Cauchy number changes. Then the exciting finding is the vibration amplitude have the linear relationship with the Cauchy number. It's important because in the future, when we change the fluid type or the temperature, many properties of the fluid and the solid will change. We can keep this Cauchy number to be the same. This analysis will help scale the parameters from experimental model to full scale. So when the fluid type change to be like molten salt or the working temperature changes, we can still do this dimensionless parameter study. And also when I make the Cauchy number to be the same, the vibration amplitude have no practicable relationship with the Reynolds number. So the dimensionless parameter, which involves the ratio of the flow dynamic pressure to Young's modulus of elasticity of the vibration rod, is so far overlooked. The simulation results demonstrate its strong effect on the vibration amplitude, and the dimensionless parameter is shown to exert a stronger influence on the rod displacement than the Reynolds number. So my conclusion is that for axial FIV, reproducing sufficient unsteadiness is very critical to trigger and sustain the vibration. Then the rod N type at this stage can reach nearly twice and is related on the difference of the vibration amplitude, and it's related to the flow direction. The eddy viscosity model is unable to reproduce the magnitude of the vibration amplitude, while the Reynolds stress model, it can do it. The combination of wave function and high Reynolds number stress model is a highly cost efficiency modeling approach for FIV, and the vibration amplitude will differ 2 to 10 times when you use different flow direction. And the Cauchy number goes linearly with the vibration amplitude and has a greater impact on FIV than the Reynolds number. The Reynolds number has no practicable effect on the vibration amplitude when the Cauchy number keeps constant. So the future developments, like I will extend the numerical methodology to the multi-rod, also some further numerical exploration into the effect of the rod tip shape. We already have some available experimental result. Also, we'd like to try a robust machine strategy to address the head wall stop issue. Some of the content in these slides have been published in the following paper. It's accepted, but still in press in physics of fluids. So if you are interested in this project, you can refer to this paper, but it only contains some of my numerical result. So if you are interested on my project, you can drop me an email or at my WeChat. We can arrange a small talk. Thank you.
Okay. Thank you for your presentation, and due to the time, we have time for maybe one quick question, if there is anyone in the audience. Okay, if not, I have several questions, but I will postpone them until after the session, because now we have time for the second speaker.
Okay, thank you. I hope to have a little talk with you.
Okay, okay, so thank the speaker again.